Hello, everybody. Welcome to the Global Composite Experts webinar series. My name is Wenbin Yu, Director of the Composite Design and Manufacturing Hub. This webinar series is designed to examine the history, present capabilities, and future of composites, with the goal to share the knowledge of composites that has been developed over the past 15 years. This webinar series was initiated by the Composite Manufacturing and Simulation Center at Purdue University. We are located in the Indiana Manufacturing Institute. All of you are welcome to visit us. We launched the CDM Hub, the Composite Design Manufacturing Hub, back in 2013, with the mission to convene and serve the global composite community by creation, education, evaluation, and sharing of resources for composite design and manufacturing. We envision this CDM Hub to become the premier resource for composite design and manufacturing. And CDM Hub provides a very powerful website called cdmhub.org for the composite community to carry out this mission together. You are welcome to join the global composite community online at cdmhub.org. This webinar series is one of the initiatives CDM Hub started as a service to the community. This webinar series is made available by our sponsors, including Dassault Systems, Cytek Solvay, and AnaSwift. We greatly appreciate their financial support for CDM Hub. We also invite more organizations to join us to serve the global composite community together. This webinar series will be recorded and made available on cdmhub.org. We will email you once the recorded video is available online. The presentation will last about 45 minutes, and we will have about 10 minutes for questions and answers. All attendees are muted. Please submit your questions through the Q&A box. For the sake of time, after the presentation, the questions may be summarized and rephrased for the speaker to answer more effectively. All your questions will be sent verbatim to the speaker for him to answer at their discretion. So next, let me ask Professor Byron Pipes to introduce our distinguished speaker today.
Ladies and gentlemen, I am delighted to introduce Professor Charles L. Tucker III. Professor Tucker is the Alexander D. Rankin Professor Emeritus of the Department of Mechanical Science and Engineering at the University of Illinois, Champaign-Urbana. He served as Vice Provost for Undergraduate Education and Innovation until 2017 upon his retirement. Tucker has a long record of original research contributions related to manufacturing processes for polymers and for composite materials, our subject of specialty. In addition, his model for fiber orientation that he developed some of the first computer simulations for mold filling, compression, and molding and liquid composite molding. He pioneered in the use of analytical sensitivity methods for optimal design of extrusion dies and injection molds. He showed that thermal dispersion was a significant effect in the liquid composite molding and showed how to model it. He also applied these techniques to compute optimal curing cycles for thermoset matrix composites. He developed a technique now patented for controlling the orientation of carbon fibers to enhance the electrical conductivity of fuel cell separator plates. He introduced computationally efficient models for droplet deformation in polymer blends based on Eshelby's inclusion theory, and used these models to show that droplet stretching statistics follow certain universal rules of chaotic mixing. His honors include visiting fellow, commoner, Churchill College, Cambridge University, honorary knight of St. Patrick College of Engineering at the University of Illinois, fellow of the Polymer Processing Science Society in 2020, and he was in the inaugural class. PPS Fellows was initiated with his introduction to the fellowship. He's a fellow of the American Society of Mechanical Engineers. He has the Outstanding Young in Manufacturing Engineer Award from the Society of Manufacturing Engineering, and many other awards in his career. Professor Tucker and I met while he was a graduate student at MIT under the supervision of the legendary Professor Nam Su. At the time, the General Motors Research Laboratory challenged us both in the late 1970s to bring clarity to the influence and control of fiber orientation in short fiber molded composites, a subject that they were just beginning to take up. Clearly, Professor Tucker succeeded in this challenge, as witnessed by the publication of his recent book in 2022, Fundamentals of Fiber Orientation, Description, Measurement, and Prediction, published by Hanser Publishers of Munich. As I said before, this book is a classic now. I think many of you will want to get a copy. We have several here in our group, and the pages are now wrinkled from all the use that it's receiving. Professor Tucker, I'm delighted to turn the floor over to you.
Thank you so much, Byron. That's for that most generous introduction. And it is a pleasure to be here today and to give this talk. I will also say, Byron, on a personal note, you have been a mentor, an example, a valued colleague, a cheerleader. You've put many opportunities in front of me professionally. I'm grateful for that for all of the years, and I'm happy to be able to say that in this public setting. So today we'll speak about fiber orientation prediction for discontinuous fiber composites. I'll say a lot about fundamentals and a little about future trends. As Byron mentioned, I recently produced this book, Fundamentals of Fiber Orientation. If you work in this field, I think if you are, particularly if you're, say, a grad student starting out in this field, I had that kind of audience in mind when I wrote it. I also wrote it for practicing engineers who are using commercial software and making orientation predictions and would like to understand what's going on inside, how to choose the modeling options and how to set the parameters. I wrote the book for all of you. And if you're a MATLAB user, then go to GitHub and check out fiber orientation tools. This is an extensive set of MATLAB functions to do fiber orientation calculations. It's got all the orientation models. It's got all the micromechanics models for stiffness and thermal expansion, all the closure approximations, Eshelby tensors, lots of tools there, and you can simply download them and use them for your own work and enjoy. I hope you find them useful. So I expect that this audience understands very well that processing affects properties of these discontinuous fiber materials by changing the fiber orientation state. And that's the reason we want to predict orientation. So as Byron often reminds me, the Holy Grail is not to predict orientation. The Holy Grail is to predict properties, and orientation is a key step along the way. So these this graph shows stress strain curves of sheet molding compound. And these samples are all molded from the same roll of SMC, but they're molded with different flow patterns. And that creates this dramatic variation in properties. So these two magenta curves in the center are molded by covering the mold almost 100% with the charge, and there's very little flow there. So the fibers in that part are more or less randomly oriented. There's just, in fact, a slight preferential orientation from the SMC machine, which you can see in the properties, but you probably can't see in this image of the fibers. The red curves at the top and the bottom are the 0 and 90 degree tests where you take that charge, cut it into 3 pieces and stack them up. So you initially only cover 33% of the mold, then squeeze down on that from the top so that it flows outward. And that creates a strong fiber orientation in the preference in the 0 degree direction, which makes that sample stronger and stiffer in the 0 degree direction, but more flexible and weaker when tested in the 90 degree direction. So these are the kinds of things we'd like to be able to predict. The first step in the prediction process is to describe fiber orientation state. So for these SMC samples, the fibers lie nearly in the plane. We only need a single angle phi here to describe the orientation of a single fiber. And of course, we don't have a single orientation, we have many orientations. So we have to characterize that. So one way is to measure the orientation of many different fibers and plot that data up in a histogram. And this histogram represents what we call the orientation distribution function, or perhaps you might call it the probability density function for orientation. And so on the sample on the right, you can easily see the big peak, implying a very strong orientation in the 0 degree direction or along the y-axis. And in the sample on the left, you see a very uniform looking orientation. And if you've got good eyes, you might just pick out that slight preference for the 0 degree direction in that data. In 3D, things are a little more complicated. And of course, if we want to do something like injection molding, we have to do 3D orientation. So in 3D, what we prefer to use is a unit vector P oriented along the fiber axis to describe its orientation. And you'll see P a lot in the next few slides. So you could alternately use the angles of a spherical coordinate system, theta and phi, and the two descriptions are related. And since P is a unit vector, even though it has 3 components, only 2 of them are independent. So 2 independent components of P or 2 angles, these descriptions can be interchanged. When we have groups of fibers in 3D, we have, again, a statistical distribution function, and the space of all possible orientations of that unit vector P is a sphere with unit radius. So the distribution function in 3D is defined on the surface of a unit sphere. And here I have colored the sphere with yellow as the area of highest orientation and dark blue as the area of lowest orientation. So if you had fibers mostly oriented in the one direction and kind of symmetric around that, but not perfectly oriented, you might see this picture on the left. If you had fibers more or less randomly in the 1-2 plane, but with some slight chance of getting tipped up out of the plane, you would see this picture in the center. And if you could look at this picture for a typical injection molding, fairly close to the mold wall, where 1 would be the flow direction and 3 would be the direction across the cavity thickness, you might see something like this. A strong preference for the flow direction, but the principal direction of orientation is tipped up a little bit to the 3-axis, spread out a little bit toward the 2 direction. So the nice thing about the distribution function is you can represent anything like this and in great detail. Unfortunately, the distribution function is very expensive to compute. And at this moment, it's too expensive to compute in kind of commercial software because you would have to compute everything on the surface of this sphere and repeat that for every node in the mesh, which can run to hundreds of thousands, even a few million in some meshes here in typical molding simulations today. So that's just more information than we want to wait around to see the answer for. So we need a more efficient description. And the efficient description is what we call orientation tensors. So let's start with a single fiber. It has its unit vector P, and we can multiply P by itself in this particular way. It's called a dyadic product or a tensor product, where the ij component of the tensor is Pi times Pj. So we have all the combinations, P1 times P1, P1 times P2, P2 times P2, and so forth, arranged in this little matrix. And if we substituted numbers in here, we would have this little matrix, this tensor, if you will, PP, that describes the orientation of a single fiber. So what's nice about that is we can now, if we have group of fibers and a distribution of orientation, we can take the average of that over all the fibers, or average over all the possible directions weighted by the probability distribution. And these angle brackets denote that average. And we'll call that thing capital A. That is the second order orientation tensor. So it's a matrix of components, 3 by 3, so 9 components. And that can describe the orientation distribution of a group of fibers. In fact, that matrix is symmetric. And if you go down the diagonal and add up the components, they always sum to 1. That's a consequence of the vector P having unit length. So that means there are actually just 5 independent components here. So these 5 independent components can describe the orientation. And that's where we get very efficient descriptions here that are useful in CAE software. We will need later the fourth order orientation tensor. So this has 4 indices, and it's formed by averaging all the possible combinations of 4 components of P to create all the components of this fourth order tensor. So this second order orientation tensor actually has some very nice physical interpretation. And if you aren't particularly familiar with this, but you're familiar with things like stress and strain tensors, a lot of what you know applies very directly. So if you saw a stress tensor with a 1 in the upper left corner and zeros elsewhere, you would say, oh, that's a uniaxial stress in the one direction. And that is exactly the orientation tensor with all the fibers exactly parallel to the one axis. If you had a biaxial stress, you would see 2 diagonal components that are equal, and that is the orientation tensor for fibers random in the 1-2 plane. So the nice interpretation here is we can look at the diagonal components here, and since they have to sum up to 1, they tell us what proportion of fibers is oriented along the 1 axis, along the 2 axis, along the 3 axis. So we look at this second matrix of components and say, oh, it's about evenly split. It's evenly split between the 1 and the 2, but there's no orientation in the 3 direction. Okay, very useful physical interpretation. In a shell layer and an injection molded part, you might see something like this, where you would have a strong 1 direction orientation, but not complete, some orientation in the 2 direction, and a low but non-zero component of orientation in the 3 axis. And we'll say more about that later. What about this off-diagonal component? How do we interpret those? Well, we know that things like stress and strain have principal axes or principal directions, and that is exactly true of orientation tensors. So when all the off-diagonal components are 0, the principal directions are lined up with the coordinate axes. And when you see an off-diagonal component that's non-zero, that's telling you that the principal directions of orientation are somehow tilted relative to the coordinate axes. And you can use typical eigenvector, eigenvalue analysis to find these quantities, and we will use that later on as we go. All right. One reminder is that the orientation tensors are partial information about the distribution function. So if I have a given distribution function, 0, 90 in the plane, that has a unique orientation tensor. And there's only one orientation, it produces only one orientation tensor. But if I only know the orientation tensor, then there are actually multiple distribution functions it could be representing. So going forward from distributions to tensors is unique. Going backwards is an ill-posed problem. And if we ever have to go backwards, we have to add some more information. We'll come to that again in the very end of the talk. All right. You can measure orientation experimentally. The current contemporary way is to use micro-CT. So here's a very lovely micro-CT image from my friend Thomas Rydell at Bosch. And this is the kind of sample that would typically be measured to determine orientation in an injection molded part. All these gray things are the fibers in the sample. The matrix has been computationally removed here. And the sample is about 2 by 2 by 3 millimeters. The 2 millimeter dimension is the thickness of the part, and they've cut this little piece out so that they can see it all in the micro CT and get the fine enough resolution to see the individual fibers. So from that, we measure individual fibers. The computer can discern that automatically, just wait for it to process. And we slice this data in layers across the thickness, normal to the 3-axis, and produce this kind of information. And for injection molding, we don't see rapid variations of orientation in the flow direction, but we do see strong variations across the flow. So we typically make plots like this, where the vertical axis is the orientation component, and you see we're plotting several components here, and the horizontal axis is the thickness direction of the part. Here's the old school way to measure fiber orientation. Many grad students in my lab looked at a lot of pictures like this and measured them by hand back in the bad old days. So this is a polished cross-section. So the height of it is the thickness of the part, in this case, a 3 millimeter thick part, and the horizontal axis is the flow direction. The dark background is the polymer matrix. The light objects are the fibers. These are glass fibers. They're almost perfectly circular in cross-section. So when they get sliced in the sectioning process, they appear on the section as an ellipse. And you can see that in the center, there are a lot of round dots telling you that the fibers are mostly oriented across the flow. And we call that section the core. Closer, either above or below that, are what look like layers where the fibers are elongated. And so they're oriented strongly in the flow direction. That's the shell. And if you look closely, very close to the upper and lower surface, you can see layers that look a little less oriented, and that we call that the skin. Here's the actual data for that part. Pay most attention to the red data, the A11, because that has this big variation across the thickness. And so there are clearly areas where A11 is greater than a half, meaning dominant alignment in the flow direction. Areas where A11 is less than a half, where it's cross-flow orientation. And but the shell and the core are not actual distinct layers. The transitions between them are more gradual and smooth. And the fact that you can look at an image like the one on the left and in your mind say, oh, I could draw a line at the boundary between the shell and the core is a combination of the way that these objects appear on the section and the way our human perceptual system works. We think we can see that, but when you look at the quantitative data, it's not actually there. So, now let's move on to talk about how we predict flow-induced orientation. So the father of flow-induced fiber orientation is this gentleman. This is George Barker Jeffrey. He was a British mathematician, an applied mathematician, and he was very interested in finding analytical solutions to mathematical problems, things like fluid mechanics and solid mechanics. Albert Einstein had published a paper about small spheres in a viscous fluid. And if you study suspension mechanics, you might know Einstein's equation for viscosity of a suspension with spherical particles. And Jeffrey wanted to extend that solution. So he studied ellipsoidal particles. These are rigid, and he solved the problem of a single ellipsoidal particle in a large body of Newtonian fluid that's flowing and deforming. He showed that in the absence of things like inertial effects, the center of the particle translates with the fluid velocity, so particles move with the fluid. And then he wrote derived equations for how the particle changes orientation. And today we write that equation this way and refer to it as Jeffrey's equation. So P is the orientation, P dot is the time derivative of orientation following the particle. So Jeffrey tells us what P dot is at any instant, and we can then integrate this equation over time to get the orientation of the fiber. W is the vorticity. It represents the rigid body rotation of the fluid. D is the rate of deformation. It's how the fluid is deforming or stretching. And this factor C is a geometry factor. And we always use C equals 1 for slender fibers when we do these fiber orientation predictions. So for a single particle, Jeffrey's equation is exact, and it's this perfect solution for that case. Now, Jeffrey's equation gives us two key rules for fiber orientation that don't even require any math. The first rule is that shearing flows align fibers in the shearing direction. So if we have a simple shear flow, like the picture on the bottom here, then it will tend to align fibers in the direction in which things are being sheared. In this movie, the red line is a fiber, the dots are showing you the motion of the fluid. And so you see the fluid motion and you see the fiber responding to the fluid motion and lying down in the planes of shear. The second rule is that stretching flows align fibers in the stretching direction. So now we have a flow that's compressing vertically, but stretching horizontally. And here you'll see, again, the fiber rotates to align in the direction of greatest stretching. Now, what's interesting about these rules is they explain and allow us to understand all fiber orientation phenomena, at least qualitatively. So I have yet to find an example where these rules do not explain the main direction in which fibers are becoming oriented. And so if you find a counterexample, let me know, but I haven't found one yet, and they're very powerful. The center gated disc, injection molded center gated disc, illustrates both of these rules. So this is a typical part to mold for a research study, but but the flow near a small gate in any injection molded part looks like this flow. So we're injecting here, and if you took a cross section, there's a no slip boundary condition on the upper and lower mold surface. The flow is moving faster in the center. That creates a shearing across the gap. The shearing is dominant close to the walls where the shear rate is high and the velocity is low. And that creates orientation in the shearing direction, which is the radial direction here. And that creates the shell layers. If you took a top view and look at this little sketch on the left, and imagine this little gray patch of material moving outward, its edges stay on the streamline, so it gets stretched in the circumferential or cross flow direction. So the stretching of that flow will create orientation across the flow. That dominates on near the midplane where there's no shear rate because there's no velocity gradient at the midplane, here. But the stretching works very strongly. So that creates this core orientation where the flow direction A11 is actually very low. And if we plotted A22, the cross flow component, it would look like this picture flipped upside down. And we'd have strong cross flow orientation. So people are sometimes a little surprised if they haven't worked with these rules before, that fibers can get oriented across the flow. Fibers do not orient with the flow, they orient with the shearing or with the stretching. And then you see in this picture that in between these two layers, kind of in this halfway in between, there's a competition between shearing and stretching, and the orientation is somehow intermediate to that. And this sample also seems to have this a skin layer. The skin layer is created by the fountain flow, but we won't go into details here in the interest of time. So the good news is Jeffrey's equation is qualitative. The bad news is it's not quantitative. And there are several problems we have to deal with to build a model that works better than Jeffrey. And the first one is that the fibers never get perfectly aligned. So here's a different data for a different injection molded sample, but with a very clear shell layer here. And Jeffrey says the shell alignment should be up here, but it's actually less. And in fact, this is a pretty high degree of alignment that you would, for what you would see in injection molded samples. So we need to back that off a little bit somehow. To do that, we modify Jeffrey's equation by adding a term for rotary diffusion. So if you look at the little equation at the bottom, if we wanted to model the distribution function, we need the flux of this distribution, and the flux is the density psi times the velocity p dot. And so there's a Jeffrey term for that you just uses p dot from Jeffrey's equation. And that tends to align the fibers and create these very high degrees of alignment. If you just let the flow run long enough, Jeffrey will tell you everything will get perfectly aligned. What we'd like to do is to create orientation states more like this at steady state. We want the equations to do this. So to counteract that alignment, we have to add something different. And what we add is diffusion. So think about what you know about diffusion in mass transfer or heat transfer. Diffusion creates a flux that goes from high concentration to low concentration. So diffusion tends to spread out peaks. So what happens at steady state is Jeffrey's terms tend to create the peak, the diffusion terms tend to spread the peak, and you reach some kind of steady state. This is the form of the term we add. So the d psi dp is like the gradient. The Ci gamma dot is like the diffusivity or conductivity. Gamma dot is the rate of deformation because we want all terms to scale with that. And Ci is the interaction coefficient. It's a dimensionless number that describes the interaction, the amount of diffusion. So this produces what's called the Folgar-Tucker model. Now, if you take this model and combine it with the orientation tensor, you can write an equation for A dot, the rate of change of the orientation tensor. And this combination and this equation allowed the creation of the first practical CAE software for modeling fiber orientation in injection molding, compression molding, you name it. So we see here the Jeffrey terms, the vorticity, and the deformation rate terms. And if you just had those equations, you'd have a perfect expression for Jeffrey's equation for a group of fibers with A dot. And then we have this interaction term with the interaction coefficient that has the rotary diffusion. So this is a very powerful tool, and it's kind of a basic tool for modeling fiber orientation. There's one important catch here, and that is that this fourth order tensor shows up in the equation. So we don't know what that is, and it's not helpful to write an equation for it because that equation has the sixth order tensor. So instead, what we do is we use what's called a closure approximation. At every time step, we approximate the fourth order tensor we don't know in terms of the second order tensor we do know. That's a whole, closure approximations are a whole subject unto themselves, but we now have some very good ones. One is called the natural closure, sometimes called the ORE closure. And I think you'll find that if you're a Moldflow user, that's your default. And the IBOF closure is the default in Moldex 3D. And these two are nearly the same. And they're both very accurate. And they're both the workhorse tools now for 3D fiber orientation. So I consider that a problem that's under control. Okay, so now we got to figure out how to set the interaction coefficient. The changing the interaction coefficient, as we said, changes the steady state alignment. So the red lines are calculations of how the flow direction component A11 changes with time in a simple shear flow, and you can see that they eventually reach a steady state. The top line is for a zero interaction coefficient, and it's not quite the steady state yet. It takes longer than this to get there, but it will produce highly aligned fibers. If we just make a very small interaction term, CI 0.002, so a fraction of a percent, if you will, of diffusion, we spread that sharp peak a little bit at steady state, and we get something pretty reasonable. And if we just increase the interaction coefficient further, the peak spreads more at steady state, and we can have a lower degree of alignment. So we can kind of dial this up and down. In practice, we expect the shell layer in the injection molded samples to be at or close to this steady state alignment for simple shear flow. So if we have one piece of data, we can use that to set the CI value. So what you do is pick out what parts of the thickness you think are the shell in the colored areas here, ignore any data in the core, calculate the average A11, and then there's a direct correspondence to that and the interaction coefficient. So this chart on the right is in the book. There's a function in the MATLAB software, Fiber Orientation Tools, that does this calculation for you. You enter the shell layer value of the flow direction orientation, you pick the curve for your closure approximation, and you get the interaction coefficient that will match that. So you can match these orientations in the shell layer. That's been very effective. There's some other ways of approaching this, but this is the very best way I know of. All right, so that's good, and it works really well for the traditional short glass fiber reinforced injection molding materials. If you have the long fiber materials where the pellets are initially pultruded and then processed through the injection molding machine, you need a little different treatment. So here's some fiber length data for long fiber PP and polypropylene. And even though you start with 12 millimeter fibers, by the time you've gotten it through the screw and into the mold, the fiber length, average lengths are much shorter. So the custom here is to say if the average lengths are greater than 1 millimeter, it's long fiber material. And that is fairly high aspect ratio still. So when you look at the data for that, you see lower degrees of alignment in the shell. However, this A33, this out of plane component, is also very low. So the fibers are kind of flatly oriented, kind of flat in the plane of the part, but not as strongly aligned in the flow direction here close to the wall. So if we put that into an orientation tensor, we'd see those two components and the rest of the components, and the distribution function would look something like this. And you can see that it's got a bigger spread in the 2 direction, but not much spread in the 3 direction. If we just took that Folgar-Tucker model and said, no problem, I'll use that, I'll just increase the interaction coefficient, use a larger than normal value, you can easily match that A11, no problem, but you won't match the 3 direction orientation or the other components. You'll produce something like this that's not quite right. And in particular, if you're getting A11 right, but if you're missing A22, you're going to miss the mechanical properties in the cross-flow direction, which can be very problematic. So what we need is to adjust the model yet again, and we do this by adding anisotropic rotary diffusion. So in the Folgar-Tucker model, the diffusion is isotropic. It operates equally in all directions tangent to the surface of this unit sphere, and it's described by a scalar, the interaction coefficient. With anisotropic diffusion, we can make that diffusion directional. We can make it stronger in some directions and slower in other directions. And to do that, this interaction coefficient gets replaced with some kind of tensor measure. We'll use C just to follow the trend of the interaction coefficient. So my student Jay Phelps and I worked out all the details of these ARD models. There's a general equation that looks like this. And this term, the top line is all the Jeffrey terms, and this thing in blue is the new diffusion term. It looks very complicated, but basically you just got to figure out what this C tensor is. So that's the choice here. So rather than choosing CI, you got to choose the whole C tensor. And the best choices, people have tried different things, but the best choices are based on the eigenvalues and eigenvectors of the orientation tensor. So we can write the orientation tensor in terms of its eigenvalues, lambda 1, lambda 2, lambda 3, in terms of its eigenvectors, E1, E2, and E3. And remember, these are the principal axes of orientation. So they could point anywhere in space, but if we know the orientation tensor, we know them. And then we'll build a C tensor that has the same principal axes, but can have different values or primary values along those axes. So in Moldflow, they offer you the MRD or Moldflow rotary diffusion model. The C looks like this. It looks like it has 4 parameters, but in fact, D1 sets equal to 1 because it doesn't really matter what that is. You can adjust CI. It turns out that the D2 the whole thing is not very sensitive to D2, so take the default 0.5 and just adjust these two parameters. So a new interaction coefficient and this D3 parameter, that's your anisotropy parameter. If you're a Moldex 3D user, they use something called the PARD, or principal anisotropic rotary diffusion, because they're using the principal axis of A, and that has two parameters as well, an interaction coefficient and this omega parameter. And so the idea is that you can use these two parameters to choose A11 and A33 independently. So if you're in the Folgar-Tucker world, you choose A11, there's only one choice of A33, you're stuck with it. With an ARD model, you can choose the A33 separately and you can get this combination that you want. And we're still talking about steady state and simple shear flow. The one warning is that not all combinations are available. And so this blue colored area is the space of all possible combinations for the MRD model. And the PARD model is bounded by these magenta lines, the solid one and the dashed one, just inside. So essentially they cover the same area here. And that does cover apparently all the points we typically see in experimental data. Good news. But I just want to make sure you understand that if you want a point like this yellow square down at the bottom, you can't get it. There's no combination of parameters that will allow you to get there from here. So with this, we can also match the orientation patterns in the shell layer, say, in long fiber materials. Good. There's one more problem we have to deal with. The problem is that the standard models miss the core thickness. They underpredict the core thickness. So here's data from a short glass fibers. The dashed line is a prediction of a mold filling simulation using a Folgar-Tucker model. And the actual core is something like this wide, but the predicted core is very different. So how do we deal with that? Well, what's going on here is that the fibers are aligning more gradually in shear flow than Jeffrey's equation predicts. So using the interaction coefficient allowed us to get the steady state, but now we got to get the transient rise rate correct. The lines in these curves are the Folgar-Tucker model to fit the steady state. The points show that the actual material is rising much more slowly. And this data, by the way, is from Don Baird and one of his students. Very careful, very useful experiment to do all these. They have to repeat this experiment many, many times to do the measurement, but it's tremendously useful data. So in order to do that, we have to slow down the orientation rate, but you got to be careful how you do it. So if you just multiplied everything by some constant on the right-hand side by some constant to slow it down, then you'd slow down this vorticity term, and that would mean that if you rotated the material in rigid body rotation, the fibers would not rotate with it at the same speed. Very weird. That would be wrong. So it took us a while to figure out how to do this. And the model we developed is called RSC for reduced strain closure, because it mostly affects the fourth order term or the closure term. So these blue shaded terms are the new terms here, and the L and M are calculated from the second order tensor, so there's nothing special there. And kappa is the adjustable parameter, and that's the slowdown factor, I like to think of it. So if kappa equals 1, you can see that we get the regular, in this case, like Folgar-Tucker version of the model. And if kappa is less than 1, then we'll see slower rise rates. And if we, for example, adjust kappa, and with the same data from the last slide, we can get a pretty good fit to that data. So that's really helpful. And this model, because it's objective, it can be used in 3D filling software, and there are no issues with getting different answers in different coordinate systems and things like that. One of the things that's remarkable about this result, about this model, is that the value of kappa is so small. And so in this experiment, kappa is 1/7. The kinetics of orientation are about 7 times slower than Jeffrey's equation would suggest. Now, I want to emphasize this model is phenomenological. That's a fancy way of saying we wrote an equation that behaves like we see the real material behave, but we didn't derive it from anything more fundamental. There is, in fact, no fundamental derivation or no fundamental theory that explains this slow orientation kinetics, this slow rise rate of orientation. And that's one of the big scientific mysteries of this field. It will be wonderful just to figure that out and to be able to predict it. But for now, we use kappa as a fitting factor. And what we typically do is adjust kappa to match core width in one experiment, and then we think we have a pretty good set of data for or parameters for that given material for any molding we might wish to make out of that material. And so here you see we can get a really good match to experimental data here with this RSC model, and look at the value of kappa, 1/20. So this slowdown rate is an order of magnitude effect and still a big mystery. If one of you would like to solve that, I would love to understand it and see the solution. So this gets us to the point of being able to predict fiber orientation very well. I want to say just a few words about the mechanical property side of things. So mechanical property predictions use what's called, for these materials, use what's called a two-step homogenization process. So if we have a material that at the micro scale has discrete fibers and matrix and maybe other things, voids or particulate reinforcement or whatever, homogenization means computing the properties of some uniform material that has equivalent, say, stiffness or strength or thermal expansion. So that's what we mean by homogenization. And conceptually, the way we do this is just we imagine decomposing the real material into pseudograins or chunks, and each one of these chunks has a simpler structure. It has, say, all aligned fibers, but of the same volume fraction and aspect ratio and so forth. And then the first step is to predict equivalent uniform properties of each chunk. These are anisotropic, so their orientation still matters for the chunk. And then the second step is to average those things together in some way to get the final result. So the first step, we used to use things like Halpin Psi. Nowadays, the Eshelby/Mori-Tanaka, sometimes called tandem and wing model, is the preferred model for stiffness. From that, you can also get thermal expansion and get good results. People are starting to use other models to try to fine-tune this step a little bit. That's an interesting and deep subject on its own. We won't go deeper into that. The point I wanted to make here is the second step is where you average over the orientation distribution. And the question is, okay, I'm a mechanical property person. What do I need to know about the orientation? If you're doing linear properties, if you're doing linear elastic stiffness, if you're doing linear thermal expansion, the only information you need are the second order and fourth order orientation tensors. So remember I said earlier, that's partial information about the orientation state, but it's the partial information you need to do this linear averaging. So these orientation tensors have a really interesting fundamental place in this whole workflow of going from processing to structure to properties. If you're interested in nonlinear properties, if you want to do like an elastic plastic model of the material and maybe work toward modeling the failure process, very challenging, but there's progress there. If you're doing nonlinear properties, you actually need to go back and reconstruct the distribution function. You need to go from the orientation tensors to the distribution function. And so in the reconstruction, I'm going to just show you an example for planar orientation here. So reconstruction means going from orientation tensor to distribution function. Remember, that's not unique. So you have to make some assumptions. So the test is to start with the distribution function. This is calculated from a Folgar-Tucker model to have very clear data. Calculate the orientation tensor from that distribution, and then try to reconstruct that function and see what you get. So when I wrote the book, I advocated for using a mathematical form called the Jeffrey distribution. That's the orientation state you'd get if you used, if you started with a random distribution of fibers and then deformed them in some way and every fiber followed Jeffrey's equation. That isn't what actually happens in the real composite, but it's kind of close to that. And so, and then you just find the Jeffrey distribution that matches your second order orientation tensor, you're good to go. It's pretty good, it's reasonable, okay? But in the last year, after I finished the book, I did some more work on this subject and discovered that you can get even better matches by using something called the maximum entropy distribution, specifically the fourth order maximum entropy distribution. That needs the fourth order orientation tensor. So you got to get that from a closure approximation. And in this same paper, I developed something called non-orthotropic closures, which click up the accuracy a little bit more here for these planar distributions. At the moment, that only exists for planar orientation. And so if you're interested and want to extend it to 3D, I think that'd be a great contribution, but there's some additional steps to take. So that's the story. We've talked about how processing affects structure a lot and how to model that. We've talked a little bit about how structure affects properties. And I hope you found that useful. And I encourage you to take a look at the book if you're interested and to check out the Fiber Orientation Tools software if you're a MATLAB user. And hope that helps you in your work. So thank you very much.
Professor Tucker, thank you very much. This is Jonathan Goodsall. I'll be handling the questions.
Yeah.
We've had a couple of comments. Some people said this is the clearest presentation they've ever seen on this subject. And I'll note that this is being recorded, will be posted on CDM Hub. Had multiple people ask, is there a way to get this? So yes, there will be a way to get this. We'll provide those details at the end.
Great, thank you.
The audience.
Yeah.
One question came up early at the beginning was on ways to treat the curvature of fibers in addition to orientation. Can you comment on that?
I can comment on it, but I don't have an answer. So, even the long fiber materials I described, and even that very first sample I showed of SMC has wavy and curved fibers. And there are a few models that consider a fiber that is hinged in the center. Those have been, people have experimented with those, but they haven't shown great promise in helping us model these things. I think at this moment, we don't have a good sense of even what the descriptors, what would the variables be to describe that. The best tools we have for dealing with curved fibers now are direct fiber simulations. So people can now do calculations where hundreds or maybe 1,000 or so fibers are represented explicitly, all together and all interacting and the fluid deforming. And those calculations can incorporate fiber curvature. So that's the best tool we have, but this is still an important and very open question.
Thank you. Mm-hmm. Someone also asked early on, in slide 12, you had a fiber orientation at the core. They're asking why that was not symmetrical.
Sure. Let me see if I can go to that quickly, since we have a moment. Yeah. So you're looking at this. Why is the core not symmetric? And the answer would be because the flow is not necessarily symmetric. So, if you have something that's injected from one side, then have a part like this that's injected from the top, then the temperature distribution won't necessarily be symmetric across the height here, and that affects the flow pattern and that affects the orientation. The other thing that may be happening in this picture, this is a long fiber material. The long fiber materials do have little clusters of fibers that stay together and don't get dispersed. You can see them, perhaps in this image, you might see something like this might be one of those clusters. It's a little hard to know. And what that does is it makes this kind of data kind of noisy and lumpy. So in this case, we may be seeing noise in the data. You'd want a bigger sample to decide if the core was really asymmetric.
Someone also asked a question around, are there threshold numbers in identifying the cores in the shell region in terms of A11, or is it generally done just by observation, looking at trends?
I don't have any magic numbers. So yeah, I'm mostly looking at trends here, I did show one data set where there's a very clear plateau in the A11 close to the wall. That's easy. A data set like this, very difficult to, this is kind of a judgment matter. What you'd probably do with a material, if this were the data you'd probably do your best to pick out a shell value, put it in the software, make a prediction, see how well it works across the whole thickness, maybe adjust it up or down a little bit to dial it in, somewhat by trial and error, by trying to match the whole data set if you have it. Yeah. Okay.
We've got now, I'm going to bundle a few questions together. They're all kind of along the theme of exploring where the model works, where it doesn't. Things like, and I'll just give you a sampling, carbon and glass, or if you had carbon and glass fibers both. If you had something where rather than injection molding, you were doing additive manufacturing. If you had large toes or bundles of fibers, and if you had nano tubes. Thoughts about where this would apply?
Nice. Okay, so first, if you go from all carbon to all glass, the model works quite well. And you just have to decide what your interaction coefficient is, or what your ARD parameters are, what your kappa is. So that you need a few experiments to get that fitted well. If you were mixing carbon and glass, I've never done that. If I were interested in that, the first thing I would do is try to see if it's possible to measure the orientation of the two fiber types individually. What's the orientation tensor for the glass fibers? What is it for carbon fibers? If they're pretty similar to one another, lump it together. If they're different, you could try giving each, you could try running two orientation models in parallel with different parameters, but I don't know if that'd be meaningful or not. That's an unexplored area. If you have large bundles that retain their coherence, then you treat the bundle as the object of modeling, of fiber modeling. So this would be like SMC and what we call hard glass fibers, meaning the sizing is strong and the bundle stays together. So that's pretty much how we treat SMC. We look more at the bundle than the filament. If you've got a really soft glass where those bundles come apart, we don't have fantastic models at the moment for how those bundles start to disintegrate. I was just a week or two ago on a PhD thesis defense from France, Francois Mahé, who I believe is on the seminar. Hi, Francois. So stay tuned. There could be some interesting developments in the future coming from there. Nanofibers. Nanofibers are small enough that they have both the Jeffrey forces and they have like molecular level forces that attract them to their neighbors. So you need something else in the model to capture that. I haven't really followed that field to know if that's like a problem where that has strong contributions or if it's still emerging. So, kind of qualitatively, you'd expect the qualitative rules to still work, but the fibers want to touch one another and stick to one another and kind of form a network. And so you would expect quantitatively that they would be different. Yeah.
That was a lot of different answers right there.
Yeah.
I think with that, we'll again say thank you very much. We've enjoyed this, and again, to everybody, this is being recorded. And check your email. We'll send you an email. Again, this was Professor Tucker. This was fantastic. We appreciate this very much. And to the attendees, we appreciate your attendance, the questions and answers. And Professor Tucker, we will send you the list of questions together with people that have asked them. So you're free to reach out and engage in dialogue.
You're right.
And with that, we'll close here today, and we'll send out a reminder for the next webinar.
Wonderful. Thank you so much.
Thanks all.
All right.
Bye-bye.